Okay, so first things first, we have to sketch y equal to sec x. So let's put y equals sec, which is 1 over cos 2x. So we have a period equal to pi. So if I sketch a very quick sine graph over that, cos graph I should say, over that period. There's one cycle, two cycles. So there's 2 pi, pi, obviously pi on 2, oops, that's not pi on 2 at all. There's pi on 2 there. So that'll be pi on 4, 3 pi on 4, etc. So now if I want to sketch the reciprocal function 1 over, what I do know is that the asymptotes occur where the intercepts are at 0, or where the x-intercepts are, I should say. So just for my first couple there, label them, pi on 4, 3 pi on 4, 5 pi on 4, and 7 pi on 4. And at those minimum and maximum values, oops, that's not a very good graph, we just sketch the reciprocal part of it. Yeah. So those black sections there are my graph. All right. Let's have a look at number 2. I might put the original graph in here because we might. So we know that this particular graph is the sine graph. So we're interested in really 1 over sine of all that. So we know it's a sine graph translated pi on 3 units to the left. So my standard sine graph, 1, -1, let's see if we can do a reasonable job of that. That's 0 to 2 pi. Since we're shifting it to the left, I might extend that a fraction further. These current values of this graph, let's just make everything over 2 pi. So let's make it 12 pi on 6. Sorry, 12 pi on 6 there at the end of the domain. Yeah. So we'll call that 18 pi on 6. And we'll call that 6 pi on 6. And then the other key values then are obviously 3 pi on 6, 9 pi on 6, 15 pi on 6, and everything is going to move 2 pi on 6 to the left. All right, so that point there goes there. We have an intercept there. That point there goes to there. That point there comes across. That point there comes across. This point here comes across. This point here comes across. This point here comes across. So my graph looks something like that. Yeah, the shape's not perfect, but that's okay. So let's just get where my asymptotes definitely are. There's one of them there. There's one of them there. And there would be one there, but it looks like that's going to be too far, isn't it? So let's just talk about where that point there is going to be at 18 less 2, 16 pi on 6, which is too big. In fact, that turning point is 2 to the left, which is 13 pi on 6, which is too small also. Yeah, so let's label our key points, if I can keep track of that. So it was at 12, back 2, so that's at 10 pi on 6, that asymptote. It wasn't 6, back 2, that's at 4 pi on 6, that asymptote. So my graph itself is just going to reflect everything to be a bit like that. We're going to go up to there. Now that turning point is probably not going to quite fit within, we decided. So the graph probably stops a little bit, maybe there for something like that. So if we want to label those key points, that turning point there was at 3 pi on 6, it's gone back 2 spots. So that point there will be at pi on 6. This one here, which was at 9, is at 7 pi on 6. So look, I know it's a little bit messy. That point there stops, doesn't it? So it stops at 2 pi. So I have to work out what 2 pi is at each of those points. So if I put sine of 2 pi plus pi on 3 is really just the same as sine of pi on 3. Sine of pi on 3 is root 3 on 2. 1 over root 3 on 2 is 2 on root 3. So I'll just write it as that. And that point there will be exactly the same. So that'll be the point 2 pi, 2 on root 3. So look, apologies for it being a bit messy. Probably should have given us all a little bit more room to work with. All right, so let's keep working on multiple choice question. The graph of fx has a period of pi and f is not defined at x equal to pi on 4 or at x equal to 3 pi on 4. So period of pi, what does that mean? Let's go. So period of pi and their asymptotes. So even if, so let's consider what the graph might be. So let's get our highlighter. So for the period to be pi, that means the period equals 2 pi on n. So n has got to be equal to 2. Yeah. So straight away, let's eliminate those two graphs. All right. Now, if I do a standard sine or a standard sine 2x or standard cos 2x graph, it looks, even if I do a sine 2x, that's pi on 2. Now, if I'm going to translate that graph left or right, at the moment my asymptotes would be there. So that's obviously sine 2x. So if I translate, I just don't see how that's going to work nicely for a cosec graph. If I'm going to translate that as 2x minus pi on 2, my asymptotes are going to be there, there, and there. So the asymptotes aren't going to work for a sine 2x graph. So let's make it a cos 2x graph. Obviously, we could just go straight to our calculator. If I'm going to go to a cos 2x, let's go that way. Cos 2x, so that's pi on 2, pi on 4, 3 pi on 4. So that's cos 2x. So at the moment I've got asymptotes at those 2 points, but we need a translation to take place. Yeah. So this one here is the same as sec x minus pi on 4. And this one here would be sec x minus pi on 2. So the only one of those that's going to work, because that's going to be at minus pi on 4. So clearly it's this one here, right, because this one here is going to only shift us pi on 4 units to the left, which will take my 3 pi on 4 to pi on 2 and my pi on 4 to 0. So it's not going to work for me. So the correct response there is going to be C. Oops. What's up here? Exact values. Okay, so remember cot. So this is just all about turning everything in terms of, making everything in terms of sine, cos, or tan. Cot is the same as 1 over tan 5 pi on 6. So let's concentrate on tan of 5 pi on 6. tan of 5 pi on 6 is equal to tan of 6 pi on 6 minus pi on 6, which is equal to tan pi on 6. So pi minus puts me in quadrant 2. So that's equal to negative tan pi on 6, which is tan of pi on 6 is equal to negative 1 on root 3. Therefore, cot 5 pi on 6 is equal to negative 1 over 1 on root 3, which is equal to negative root 3. Do the same thing for sec. So sec, we have to focus on cos. So let's talk about cos negative 5 pi on 4. Negative 5 pi on 4 is negative 4 minus 1. So it's there. So that's really equal to cos of 3 pi on 4, which is equal to negative cos pi on 4, which is negative 1 on root 2. Therefore, sec of negative 5 pi on 4 is 1 over negative 1 on root 2, which equals negative root 2. Let's keep working through. Exactly the same thing again. So sec is the same as 1 on cos. So cos 2 pi on 3 is equal to cos pi on 3. So it's pi minus pi on 3. So it's negative, which equals negative a half. Therefore, sec 2 pi on 3 is equal to 1 over negative a half, which equals negative 2. Cosec is all about sine. Sine 7 pi on 6 is equal to sine pi plus pi on 6, but it takes into the third quadrant, so it's going to be negative. And negative sine pi on 6 is negative a half. Therefore, cosec 7 pi on 6 is equal to 1 over negative a half, which is negative 2. A couple more to go. Find cos, sec, sine, cosec, etc. from our tan function. I think the easiest way to do these is always with a right angle triangle. So if I make this angle there x, tan is opposite over adjacent. So opposite over adjacent, because tan x equals 2. And if that's the case, c squared plus b squared, c squared equals a squared plus b squared. So that has to be root 5. All right, so now cos x, keeping track of the quadrant, everything's in the first quadrant. So cos x is equal to adjacent over hypotenuse. Sec x is equal to 1 over cos x, 1 over 1 on root 5, which is equal to root 5. Sin x is equal to opposite, which is 2 over hypotenuse, which is root 5. Cosec is 1 over that, which is root 5 on 2. We've got nothing else underneath there. Okay, so that's the end of that one. Example 5, a little bit of simplification. Simplify each of the following. So let's, I guess, this is the one that we get. And then if I divide everything by cos, sine over cos is tan, cos over cos is 1, 1 over cos is sec squared, gives me that one. Or if I divide everything by sine, sine over sine is 1, cos over sine is cot, 1 over sine is cosec. So it all comes from the same identity, all right? So tan squared x plus 1 is equal to sec squared. So let's just maybe make it a bit bigger. So we get sec squared x over tan squared x, which is the same as, what's sec? Sec is 1 over cos squared x divided by tan, which is sine squared x over cos squared x. Flip it upside down and multiply. Squared x times cos squared x over sine squared x. 1 over sine squared x, which is cosec squared x. Okay? Cot squared minus cosec squared. So where's our identities up there? So I've got cot squared. Well, let's have a look at cosec. Cosec is 1 plus cot squared. If I just do that, so what does that mean? So I get cot squared x minus cosec, which is 1 plus cot squared x equals cot squared x minus 1 minus cot squared x, which equals -1. So it actually works out rather nicely for us. What about sine squared minus sine of the 4x minus cos of the 4x? It looks a little bit like a squared minus b squared, doesn't it? So what if I write it as sine squared x squared minus cos squared x squared? Then I do have one term squared minus another term squared. So then that equals a plus b times a minus b. A plus b is 1, so that gives me a sine squared x minus cos squared x. Now, if we remember our double angle, that's pretty close to one of them. But if we're not completely sure, let's change sine cos squared x minus, well, cos squared is the same as 1 minus sine squared x. Sine squared x minus 1 plus sine squared x, which is equal to 2 sine squared x minus 1, which is equal to cos 2x.